memory, DSP, and IPs. The generation of IPs means intellectual property. For example, I need a special function like a processor. No need to build the processor by yourself. Just use their IP. But here we have some restrictions. IPs, not all IPs is free. The IPs come from the companies. You have to pay. Okay? Some of them free, or you can build by yourself. As I already taught my student, this semester, I taught my student how to do the IP in GDB. So they finished the GDB by doing IP code. Yeah? So I taught them how to do the IP by themselves. This is a free IP. Everybody can use it, and they can give to their friends and colleagues. Yeah? So this is the era of IP also. Continue now. This is the last one. I just picked brief for you. So we have also soft code and hard code. Meaning of soft code, for example, anybody hear about NIOS 2? NIOS 2 is an embedded processor, soft code processor from Altera, I mean Intel FPGA. While MicroBliss is an embedded processor, same soft core, but from Xilinx, a different company. Because now the dominator company before is Altera and Xilinx. Both of them. Now Altera part of Intel FPGA, so the dominator is still Intel and Xi. Okay? So I deal with them both, early and until now. Clear? So those now soft core embedded processor, one of them NIOS 2 or MicroBliss. Soft code, that means it's not exist inside the FPGA as a hard component. It's just soft component in the tool. You reconfigure, that means you send to the FPGA. It's not exist as a hard component, not physical component. I give you just simple example. If you still remember the principle of computer architecture,
there are many different ones.
Sure not. Anyway, so we have, and anybody know? Do you hear about virtual memory? You hear about, right? This is any computer, any user can know virtual memory, right? Virtual memory is a RAM, but not physical RAM. It's a RAM, extended RAM from the hard disk. That means your RAM not enough to serve the application and the Windows. So the operating system doing what? Expand this RAM logically from memory, from the hard disk. So hard disk, part of hard disk, small part, will become RAM for you. This is we call virtual memory. Okay? So another term, inside the processor, we can hear also logical register and physical register. Physical register mean exactly hard register inside the processor. While when we say logical register mean location in the memory. Clear? So it's not a register. It's just location inside them. Same here. Soft code, it's not hard or physical component inside the FPGA. It just soft code or soft module will be sent from the CAD tool, for example Altera or ISE from Xi to FPGA chip. Clear? This is a soft code. Go to the hard code. Hard code is physical component. Like now, before they create the processor, embedded processor, they call it PowerPC. If you hear about the PowerPC, it's an embedded processor but hard code. They put inside Xi, Spartan or Vertex from Xilinx. In Altera, they put ARM processor, Cortex. If you know, if you go to the Explorer in Google, you will write just FPGA SoC. So you will see, oh, FPGA SoC means there is a hardcore ARM processor inside FPGA. That means hard processor is not soft. It's a physical component inside the chip. Clear? And we can use by what? by programming C, C++, and assembly as well. Okay, so this is open our mind. Oh, FPGA, we can use C or C++? Yes, surely we can. Okay, we can use. If we're using embedded processors, either soft core or hard core, still we can use another language, not HDL language. It's a high-level language, C, C++. Clear? So this is the generation of FPGA in brief. Okay. Hopefully now you get just an idea about the FPGA. So where we are in this technology. In technology we have, for example, general purpose processor like i7, any processor, i3, i5, all this considered general purpose, right? Programmable DSP, TMS, you know TMS? It's a Texas Instrument processor. It's just for DSP, okay? So this is a more specific. Then reconfigurable devices technology. One of these reconfigurable FPGA. Clear? Then the lowest one, ASIC, application specific integrated circuit. So this is the specialization, this is the programmability. The high level of programmability given by general purpose processor. While the high level of specification given, specialization, given by ASIC. If you ask me, okay, we didn't see ASIC. No, you see ASIC every day. Okay? A processor consider ASIC, right? But after they finish the design, they send to become as a chip for you. For example, you do your development by using FPGA. After you finish, finalize your project already optimum, there is no add-ons features, you send your design to ASIC factory. They do your design as a chip, and your chip will be sold as a chip, fixed architecture. So that means after we finish everything, we send our design to the ASIC company, Silicon Valley and so on. They do what? They do chip for you. You can sell this chip as a fixed architecture. Clear? So the last stage after development, ASIC. Clear? But after you finish, in the ASIC production, you cannot change anything. Any mistake will cost you too much. Yeah? You cannot change anything at that point. You have to change the design and resend again and lose thousands of USA dollar and so on. Yeah? So we are here, reconfigurable devices. One of them, FPGA. Clear? So this is just an example about the FPGA. You see this is the family, Altera family, like Cyclone, okay? Cyclone, Era, and Stratix, and hard copy. Then this is come from Xyl, like Vertex, Spartan, and so on. This is the lattice one after already overcome the Altera. The Altera already sold to the Intel, so they produce Intel Stratix. Actually, it's a Stratix. Before is Altera Stratix. Now become Intel Stratix. Just the change. Okay, and this is the lattice FPGA chip. Okay, till now already inside 5.5 million logic elements. In addition, for all this, I already explained to you like memory, DSP component, cores, hardcore, and so on. Clear? So this is one. Which one? This is what we call it three-dimensional design architecture inside your chip. Clear? So I will show you later on. Stratix 10 already three-dimensional, not just one dimension. Okay, of projection. Then we will see in a few slides. So now go to Industry 4.0. So what is the Industry 4.0? Everybody know the industry, right? But 4.0 means the industry become more smart. Okay, become smarter. Actually, we can connectivity. How everything inside the factory connected together, not just inside the factory, to the other branch of the same factory or the other companies. So the term here, connectivity. Okay, how the factory connected with the others. Yeah? So to connect with the other, we need a lot of things. Okay? I'll not talk about the autonomous here, I mean robotics inside the factory. So robotic already exists. The only thing we have to add what? The connection between robotics and the others. Clear? So robotics not in our concern now. Just I'll talk about the industry 4.0. Clear? So we will explore. To become smarter, we need cyber-physical system, IoT, and cloud computing. Why? Because everything will be sent to the cloud. We will share our information. Any damage, any defective, any problem happen will be shared with the other branch and other companies. Okay? Sure, with the secure links. Okay? So we will explore this. So smart factory and even more. I'll show you one video now, just simple one. Okay, after this slide. So this is industry 4.0. Will tackle all of this parts, starting from the autonomous robots, I mean the machines, arms, and so on, and all this until we reach the big data. Okay, so we will go and see.
History class taught us about the Industrial Revolution, when steam power changed how things were manufactured. But there hasn't been just one industrial revolution. The manufacturing industry has reinvented itself many times. The first industrial revolution is the familiar one. Beginning in the late 18th century, manufacturers used steam engines and hydraulic power in factories to make production more efficient. The second revolution began in the late 19th century, when electricity and assembly lines made mass production possible. The third took off in the 60s, when advances in computing and eliminating unplanned downtime in the factory, ensuring you never start work on the production floor that can be finished with the material, labor, and machines you have on hand, tripling the leverage you get from costly support labor and specialized tech talent, changing the dynamics of your channel and creating new sources of revenue, enabling your products to sell services for you, growing your data business as big as your product business, using customer and channel connectivity to achieve unprecedented levels of customer service. And the changes for the industry as a whole will be even broader, as broad as we've seen in past revolutions. Industry 4.0 will change the basis of competition, alter how manufacturers win customers, shake up the structure of the manufacturing industry, and give you the opportunity to make history.
Okay, so this is just short introduction about the industry 4.0. Thanks Google. You can find everything in Google, right? It's not mine. Okay, just I utilize. Okay, as a user. Okay, so by the way, the same slide already presented on this neck board. Okay, here. So now we'll start to design or to use FPGA as a professional people, professional engineer. We have to tackle two things, to know two things. The CAD tool, the software part, to develop our design, to create our design. And the other part, to know the architecture of the current device we already use. For example, anybody now, all of you using, most of you, those in computer programming side, even if you are engineer, you're writing program in C or C# or Java, right? Okay. If I ask simple question, did you read the architecture of your processor, i7 for example? Did you know what is inside the i7? Sure. Most of you or almost nobody read it, right? So when you're going to write the program, you write, okay, open the compiler, whatever Java or C# or C++, then start to write, right? Copy from here, then modify and so on. Then you create your program. Then you graduate to become PhD. Okay? This is okay. But this is as a user. Why? Because before you start to write a program, you have to know the architecture. So if I ask now, how many CPU inside i7? Anybody know? 7, huh? Because i7 means 7, right? Any other number? Actually, no, just 8. Clear? So inside i7 or i5, we can find 8 CPUs. You see, I say processor and sometimes say CPU, right? So CPU is part of processor. Processor different than CPU. Processor, the big envelope. Inside the processor, we have CPUs, caches, microprocessor, coprocessors, and buses. Clear? This is the processor. CPU is a part of your processor. So when you write the program in any language, you have to know the architecture first. So you can write in multi-threading approach. You divide your program to threads and distribute among the CPUs. Now when you write, most of your program already executed by one CPU inside the processor. That means, especially maybe we have exception for those working on multiple programming. Maybe they touch this part. I don't know. They have to look again after this talk. Okay? Because when you write multi-threading, that means you have to distribute your thread among the CPU. That's it. Otherwise, your CPU is already wasted. Okay? Clear? Why I'm saying this? To design on FPGA, you have to know, okay, I'm designing with DE2 board, for example. DE2 board have Cyclone 2. If I'm designing using DE1 SoC, it's have Cyclone V SoC. So different chips. And both of them FPGA, but different chips. What is inside Cyclone V different than the Cyclone 2? There is common, yes, both of them have logic element, right? But memory side different. The architecture itself is different. Clear? So when I'm going to design, I know, I have 4 PLL, so I can utilize 4 PLL. Okay? I have how much memory inside Cyclone V? Yes, I can utilize this part. It's not enough for me. So I have to change to other chip. Clear? Some of you, or most of us, do what? Design after reach the final stage? Not enough. But you have to know this is from the early stage. Otherwise, you are not professional in design. Clear? So I hope you will change your view when you design. Start to design. You have to study first your application and needs. What is the requirement? Then what is the proper chip for you? Okay? What is the proper CAD tool for you? Some of you just using, those using FPGA, going to use, Altera or Intel just released 17.1, the Quartus 2, the latest version of CAD tool. So I'm going to use it. Why? Your application need this CAD tool? No. Okay. Did your laptop support this version of CAD tool? Support, that means can run smoothly, or just when you open or wait half hour to run, to just open the Quartus. Then if you compile, take 1 hour, because your laptop specification not enough to tackle what? The Quartus version itself. So we have to be professional. When we choose something, choose it. Another side, if your application just need Arduino, just use Arduino. Don't need to go to FPGA. Some people, some engineer or some student saying, okay, I have application, so I'm going to use FPGA. So first question I'm asking means, did your application need FPGA? If you justify, that's good. If you cannot, just say, I use because I like. Like, not enough. Clear? Like is not in our term as engineer. Clear? So we have to look again about the software and hardware. So I'm starting with the software. Here, we'll start what is the trend of the industry. Clear? So everything in industry increase now, become more fast. We in terms of production, in terms of processing, in terms of marketing, and so on. Clear? So we have to cope with these demands now. Demands mean I cannot use just Arduino because it's easy to use by me, okay, to tackle something high speed. Okay, Arduino can tackle how much frequency? Let's say 16, okay, 50 meg maximum, for example. Okay. Go to the Raspberry Pi. Sorry for Raspberry Pi. Raspberry Pi, okay, but still maximum 700 meg or 1 gig. It's okay. Then after that, so the application beyond this cannot be tackled by these technologies. Yeah. If we go to the FPGA, there is a necessity to go there. Otherwise, just use the lower technology. Yeah. So this is what we have. The red one is the delay of the project. Why? Because every year the company is producing FPGA. They produce also what? Not just the hardware. They produce for you the software. I mean the CAD tool. We call it CAD tool. Okay, to make your design is faster, easier to design. As I said to you early, I start with DOS. There is no Windows. Okay, so I design under DOS. I don't know if you know DOS or not. Yeah, sure, the lecturer knows. Student maybe don't know. Okay, about the DOS. So command line. In Windows you go now command line. That means I'm using command line to design my FPGA. How much difficult, how much time I take to just finish simple circuit. Yeah. Anyway, so every year they produce new CAD tool. They increase, add on the specification, and make it easier to go to the market. No more delay. Okay, no more delay. So this is the challenge that we have. The hardware also growing up as FPGA chips. So the software also have to go with the hardware, like operating system and processors. i7, we need operating system tackle this processor efficiently. Okay, clear? So the software and hardware going together as a parallel line. Because the challenge in the hardware, if I ask you which one is the faster solution, the hardware or software? If you're going to solve problem, which one is fast, hardware or software? Software, you know? Okay, very good. Hardware. If I'm going to solve, I mean, not to design, going to get fast response performance come from where? The hardware or software? The fast one is the hardware, not the software. Clear? So hardware is more fast than software. Clear? So this challenge of the new chips of FPGA increase the demand to update or to upgrade every year the software, the CAD tool, to use the FPGA itself. So this is the software vision. Then they come out with what we call Quartus 2 Structura Q engine. Now, after 14, version 14, Quartus 2, I'm talking about Altera and Intel FPGA. After 14.1 version, they come with the Quartus Prime. Okay? 15.1 and beyond. They reached until 17 now. This year, just 1 month ago, they released 17. Okay? So, those 15.1 and beyond, they have Spectra Q engine. What is the Spectra Q engine? Totally enhanced CAD tool as a compiler. Save your time to compile your design. Okay? I try after, for my PhD, I used Quartus 11, okay, at the time. So Quartus 11, when I compile my design, it's about multiprocessor and multiple filter at the same time. So take sometimes hour to compile. Yeah? I just take the same design, my design, and try by 15.1 and 16.1. Okay? It take, you know how much time it take? Just 5 minutes. You see? They say, why? Because the algorithm used to compile your design is different now. Okay? They use fast algorithms. They use what we call cumulative. Okay? For example, you change in your design. Normally we change during the design, we change many times, right? When you compile again, the early version compile all design. Now, no need to compile all design. Okay? They compile just the part you change. Not you decide. The compiler, no, you just change this part. So the compiler will compile just this part and complete with the other design. Clear? So this is the new trend of the CAD tool. Clear? So faster entry, faster planning, faster iteration, fewer iteration, and faster debugging. Very easy to detect where is the problem. Okay, by using Spectra Q engine. Clear? So this is the more detail. I'm trying to go briefly the shield. Okay, because cannot complete by 1 hour. Just about the quarters. Okay. So this is the feature already enhanced, and we get better CAD tool now. Clear? So this is the Spectra top level design. Okay, as a software, as a CAD tool. Okay. So the quarters to Spectra Q engine here. We see the IPs. Those IPs, for example, if you using in your design, you need IP, the new IP, or update the IP already utilized by yourself. As I said to you, if you compile, no need to compile whole design. Not you, just use cumulative one, so they will compile the part you already changed, that IP you already replaced or modified. Clear? So this is the beauty now, the beauty of FPGA. Clear? So another one, the iteration. Now can the quarters to Spectra Q engine can work on different computer. That means you have one computer to design, the main one, and you can distribute. You have very big design. You can distribute this compilation among many PCs as a node. So this can all compile part of your design and at the end give you one configuration file. The configuration file means the file that you have to send to the FPGA. That means your design. Clear? One configuration file. Clear? So we faster iterations. Then we go fewer iteration. Yes. Why? Because we just compiled the changed one, updated one. Okay. Go to the also fewer iteration. I'll try just to give you fast look. Faster planning. Now, early also we can do. We can do we call it floor plan. We can arrange our design on chip by ourselves. Now normally you do compile, right? So the compiler, the CAD tool, will arrange your design on the chip, right? Put this block here and this block here and so on, and do connection routing, right? This feature you can already done by you also, but need very professional utilization and very professional knowledge from you, because the compiler choose the best according to the algorithm already implemented in the CAD tool. But sometimes, as a designer, we have our sense to make. Oh, I feel I think if I put this module beside this module, become more faster, right? Clear? But from my experience in this, because I used this before, floor plan, in my PhD. So when I try, even I worked 20 years on this field, I try to make it logically arranged by myself. But when I compile, at the end, I didn't get any extra time consumption. Yeah? That's mean the time done by compiler still better than mine. Clear? Why? Because the algorithm they use is very efficient. Okay? Clear? Sometimes when you have bulk design, yes, very difficult to do that. Why? Because as we know, the FPGA have, for example, we cannot utilize 100% of FPGA. If you want high performance, theoretically they say you can utilize all, right? Practically, I'm saying to you, until 80% of utilization, you are in the good performance. If you go beyond 80%, your performance will go down, drawback. That's mean, if you have 50K logic element in your chip, and you utilize, for example, 30K, still okay. If you utilize 45K, that means your performance will go down. Why? Because theoretically you can use 50K. Practically, due to the routing problem, because at the end, the logic element, not the only problem. The other problem is the routing. Logic element enough, but routing later on will add delay for your design. And I'll show you how they overcome this problem in a new Stratix 10. Clear? So this is about the software, how we do faster planning by using the ready IPs, ready cores, and so on. No need to build everything from scratch. After 20 years here, I'm working in this field, I have a lot of library in my PC, okay? My laptop. So now if I have any new design, no need to start from zero. Because I have all design already, just I need to utilize them or modify them to tackle the new application I want. So after you work in this technology for a few years, you will have this. Same when you're working on Java or C++ or C#. When you do some programming, later on you need to do another application. Yes, still some program you did before. So you can utilize. Clear? So this is we call sustainability. How we do reuse of our design or others as well. Clear? So this is the faster planning as well. And so I'm just going quickly. Now, for those very weak or don't want to use the HDL, they are happy with C++. Yes, we give you this, the Altera or FPGA, they give you the platform to use it. Okay, by using what? Embedded core, either soft or hard core. Like ARM as a hard core or embedded as a NIOS or microblade. Clear? So if you don't like FPGA, I mean the HDL, either VHDL or Verilog, you can use C or C++. But at the end, you still have to write some VHDL or Verilog. Just little portion of your code in HDL. Just a cover for C++ and C program. Clear? But now, very easy to use this. Then we can use C++ and so on. DSP builder, for those not in computer engineer, they don't know, they don't want to do any programming. Very easy. They give you DSP builder or system generator. In Xile, they call it system generator. And DSP, I'm trying to explore both technology for you. Xile and Altera, I mean Intel. Xile, they call it system generator, while DSP builder in Intel FPGA. Means, if you have, you know MATLAB, right? So, if you have MATLAB and you install the DSP builder, okay, you will get some module blocks inside the MATLAB, okay? We can see the sign on each module is related to FPGA. So that means you can build your design by using this module, just as Simulink. You know the Simulink in MATLAB? So just use this, connect as a blocks, then after you finish everything working well, use DSP builder to generate what? The HDL code, whatever, VHDL or Verilog. Because at the end we have to send HDL. Okay? Clear? So when you generate by using DSP builder and everything okay, you cannot touch VHDL or Verilog, the HDL generated by blocks. Why? Because the written one already converted from block to HDL by machine, by compiler. Clear? So it's totally different than you learned. If you know how to write VHDL, you write VHDL in different way. Machine generator is different than, okay? So you cannot touch, believe me, okay? So either you start with DSP builder and complete your design, or you start just by VHDL or HDL, very long. Clear? You cannot say, okay, I generate by DSP builder, then modify the HDL. Sure cannot. If you want to try, just up to you, but maybe you consume 3 years and you do nothing. You do nothing. Clear? So this is extra tool for those who want to use FPGA without touching the HDL indeed. Okay? So the entry here, we have software designer, we have embedded designer, and we have hardware designer. And then we don't know what we're going to have inside the FPGA. Clear? So high level of design compiler is already compounded by those three topics. Clear? So now, going to explore more deep. I'm going to do SOC. I'm sorry, maybe I'm taking more than 1 hour, okay? Just 30 minutes extra. Okay? Up to you. If you want, I can cut by 1 hour. Okay, so to do SOC design, we have to use QSys. Okay? QSys, that means the system we can utilize inside the FPGA by using the QSys tool. Actually, we call it System on Programmable Chip. Yeah? System on Programmable Chip. The early version, they called SOPC. Now, we're using QSys. So when we're using QSys, there's just we do utilizing of this module, mega cores or hard cores, soft cores, sorry. Then we put in the map. Then we ask Quartz or the CAD tool to generate the file, the netlist for us. Then we can utilize on FPGA chip. Clear? So QSys is one of very important tool inside FPGA technology. Clear? So now, to conclude, it's not just before we just use pin planner, pin assignment. Now we can use blueprint. As I said to you, flow plan. Okay? Files is not just one file. Now we have cores more than file itself. Then desktop, before we can use just our PC. Now we can use multiple PC to compile the same design. This is by Spectra Q engine. Okay? And the last one, before we just use, for example, HDL, now we can use more than HDL, C, C++, and so on, or OpenCL. Clear? So we have different language, not just HDL. Okay? So now I'm going to explore the Lattice hardware. The Lattice hardware here, I took just the 10, generation 10 from Intel FPGAs, Max 10, Era 10, and Stratix 10. I explored Stratix 10 with you is more because it's more advanced. This is the 3D dimension one. Okay, 3D dimension, that's mean all this is the logic element, 5.5 million we have, okay, inside. With all of this additional feature, like for example, 14 nano, this is the scale of fabrication, 14 nano. Clear? For those working in IC design, they understand the meaning of 14 nano. That means the scale of our the chip fabrication. Okay, this is the hardcore processors inside the chip. This is the power consumption. Okay, is already decreased, and because normally Cyclone 2 we use on DE2 board is using just 1.2 and 1.8 volt. Clear? Cyclone 2. Stratix 10 is just used the lower level. So it's almost green. So the power is reduced. Why? Do you know why? When you compile and use your design, then utilize one. If you have pipelining inside Stratix, if this pipeline is not active, will be not look like idle. So they reduce the power. You remember when you use your chip full capacity, yes, the power will be increasing. Okay, how much power will be increasing. But if you use just one pipeline from 10, sure, the power is less. Okay. Security, yes. Security, yes. We working in Word, they can hack your design. So this is more secure. Now, before also in CPLD and in some FPGA, and currently also as well, we can lock our design inside the chip. Okay? That's mean, because if your design inside the chip, there is a possibility to read your design from the chip. If we read your file, still we can copy your chip, copy your design. Clear? So to protect this, they put like a password, a protection. Okay? So your design will be protected. Nobody can take it. Okay? You make it look like near to impossible for them to hack your design. So it's more secure. Okay? So this is all feature of Lattice 10. The most one I want to highlight, HyperFlex register or architecture. The meaning of HyperFlex architecture, I'll go directly to the point. You see this is the blue dot. Actually, this is, we call it registers. After a few years of fabrication for FPGA, they realized the routing delay is more than the register itself. That means, because normally we know there is two type of delay, propagation and secure, right? And if I ask you which one is the higher one, normally we say propagation delay is higher than secure delay. Secure delay means the delay on the wire, while propagation delay means the delay happened because of response or processing of the component. Clear? For example, if you have two input from AND gate, sure at the T0, sure you cannot get the output at T0, right? Should be you get the output at T1, right? Sure, cannot at the same time, right? So this time we could delay between T0 and T1 to get the output, we call it propagation delay. While the time taken to transfer signal from point A to point B through track or wire, okay, this we call secure delay. And normally the secure delay is less than propagation. Clear? Because propagation will depend on switching, transistor, and so on. While secure is just the line delay. Now in FPGA, the HyperFlex technology or architecture, the register is faster than the routing itself. So I'll show you here. So you see this between two ALM. ALM means adaptive logic module. Between of them we have 3.5 nanosecond delay. Just routing, just wire here. Okay, inside the chip. So while after we add the HyperFlex, the maximum for one register is 1.2 nano. Clear? So now the register become delay in the register is less than the delay in routing itself. Clear? So this HyperFlex technology increased the speed of the processing inside the FPGA. So the Lattice 10 become faster and faster. Clear? So this is what I want to highlight in this hardware. So TX mean all these you see the comparison between Lattice V, Lattice 10 and improvement factor. You see all is almost double or triple. But I just want to highlight this is without PLL. This is the normal one. If I never touch PLL. For you, if you don't know PLL first phase loop. If you want to divide the frequency, what we have to do? What we have to do if we want to divide the frequency? We have to use the flip-flop, right? So if I enter 50 meg to one flip-flop, the output become 25 meg, right? So divide by 2. So each flip-flop divide by 2. So if I want to divide by 8, I have to do what? How many flip-flop? 3. 2 to power 3 give you 8, right? So 3 mean I have to put 3 flip-flop cascaded one. If I put, for example, X frequency, the output become X over 8. Clear? Because each flip-flop considered by 2. This is the division. But if I'm asking now how to multiply the frequency, sure, cannot multiply frequency by yourself. So we have to use what? The low-level circuit, we call it PLL. PLL can divide, so it can multiply, and sure can divide also, can multiply the frequency to the certain factor according to the chip you already use. Okay? So this is without using PLL, we already double and triple the speed for optical transport, okay, wireless infrastructure, data center acceleration, and signal processing. So all these already double or triple. Clear? By Stratix 10. Clear? So this is in terms of power. Okay? Already we save the power compared with the 5. Then this is the enables of higher FPGA adoption in the data center, how we can utilize in data center by using DDR3, and now we can use DDR4 as well as an IP core inside FPGA. Clear? So this is also in terms of the power and area saving, okay, because we're talking about 5.5 million, okay. This is what the heterogeneous 3D SIP, system in package. Okay, system in package. Now we have multi-layer 3D dimension inside the chip. Yes, the chip is very small, but inside, because we're talking about 14 nanometer, so it's very small scale, but in 3 dimension, or 3 dimension of implementation inside. Clear? So all this increased, okay, as I already explained before. I'm trying to go fast through this is the heterogeneous also 3D system on system and package. Okay, so this is the security of this Stratix 10 and so on. Embedded processing, we can still use embedded processor, either hard or soft. Yeah? But from experience, soft processor like Nios 2 still can utilize, but the maximum can reach is 195 megahertz, the speed. So if we're talking about the high-speed application like signal processing, image processing, tracking, navigation system, jamming system, Nios 2 is not suitable. I never mean you cannot utilize. You can utilize, but you will have problem in the performance. So if you have a critical, my advice, if you have a critical application, just go to the hardware solution rather than using embedded software. That's mean using the ARM better than using Nios. Yeah, because the ARM is a hardcore component inside the FPGA. Clear? So this is the DSP component as well inside the Stratix 10. Okay? So all these features already there in Stratix 10. So the challenge is now becoming more and more. Okay? The potential is more, but still the challenge is already increased. So now go to some application like vision, intelligent vision. We start with the old one. If you remember this robot already sent to the Mars. Okay, so this is the old version of the intelligent vision. Okay, already utilized FPGA inside. One of my observations during the war before, we just got we call it UAV airplane, like airplane autopilot one without pilot. Okay, so when we open, there's inside just cameras like IR, night vision camera, day camera, and so on. And also, sir, when we see inside, just one board like this, FPGA board, okay, special board, not D2 or others, control everything. There's nothing inside, no much hardware, just board, and sure, there's a processor and so on. Yeah, on the rest, camera, sensor, and even the missiles already launched by this board. Okay, so that's mean everything we can now we got low scale technology in nano inside the chip, but in the same time we can also go low scale in the board itself. Rather than we before using very big board, now we're using very small board with the high density of logic and high performance inside this board and technology. Clear? So going smaller and with high performance. Clear? So this is the some application, if you can see, okay, about the intelligence, how we can utilize this FPGA intelligence application. For example, how we can divide our problem to the pipe planning. Okay, with full respect to the dependencies. Clear? Dependency, that means the others cannot be, if depend on the other task, cannot be executed at the same time. But still we can do pipe planning for those independent tasks. Okay? And so on. So this is how we utilize. Because the only technology give you true parallelism, FPGA, reconfigure. One of them, FPGA. We cannot say, if I ask you, a microprocessor i7 can give you true parallelism, maybe you say, oh yes, because have 8 CPUs, so it's a true parallelism. No. Still there is dependency according to the shared memory and distributed memory, and buses as well, right? So there is no 100% parallelism, correct? When I'm talking about true parallelism, that means inside FPGA we can build different engine totally independent on the others. Clear? That means the resources all is cut. They are not sharing the resources. This is we call it true dependency or true parallelism. Clear? True parallelism, the only technology can do or satisfy the high level of true parallelism, FPGA, and reconfigurable technology as well. Clear? So I'm trying to explore this terminology with you. You see how we divided the problem in different sectors inside the FPGA itself. Okay? So partitioning our design, yes, sure, we can do partitioning according to the logic element we have and cores already inside the chip itself. Then we can, as I said to you, in addition to use the HDL, we can use other language like C++ or OpenCL. Okay, these two languages can be used by user, us, to utilize the FPGA itself, not necessarily use HDL, Verilog, or PADL. Clear? So now example of FPGA, intelligent vision, like you see this ADAS, the smart car, the intelligent car, okay, how we utilize all those stereo vision, e-mirror, and so on, how we utilize all such stuff. The problem is this car needs fast response and safe, right? Because it's not a human. Can decide for you. Okay? Still they are in the early generation. Still we are in the beginning. It's not completely autonomous. Like, for example, now Tesla, they're using GPU, graphical processor unit. They didn't use FPGA. Yeah? So they're using GPU, but till now we cannot say 100% safe. Why? Because still depend on the image processing. And sometimes image processing cannot decide correctly. Yeah? So still in the beginning, but still, for example, auto parking stuff now is already utilized, already exists, and growing up this field, this application, growing day by day. Okay? So smart cities, okay, how we can monitor all these inside the city, how we do automation inside city, monitoring or any utilization for machines inside the city. Okay, data center, for example, applying the deep learning algorithm. This deep learning algorithm is actually AI algorithm, artificial intelligence, and this algorithm already used by NVIDIA company in GPU to do Tesla on car. Okay, they're using deep algorithm, deep learning algorithm. If anyone using the Lazada, Zalora like this is they're using almost deep learning algorithm. Okay, they're using how to find the information quickly. Okay, through very big data. Okay, clear? And so on. So this is also about the stereo vision application and so on. Some tracking and navigation system and so on. Clear? So this is a combination of application. This is some companies partner for using the FPGA, internal FPGA, and so on. So this is the summary about the intelligent vision. More and more become more high performance because of what? Because of the technology we have in either software and hardware. Software in terms of the CAD tool, hardware in terms of the FPGA chip itself. Okay? So going to the other applications like embedded applications. So we can see the market trend, okay? And we see the now example, for example, this is the industry now. One, how we can utilize, make it more smarter, industry 4.10, okay? How we utilize the cloud, how we utilize the big data, how we utilize the link connectivity, and so on. Okay, so all these potential allow us to make it more, make Industry 4.0 more applicable and very easy to reach in near future. Okay, because now we just have Industry 4.0, but not all the industry is considered smart. Yeah? So this is the application as well. I'm just sharing with you. This is the some application in FPGA and so on. Like PLC become more smarter and motors as well. Okay, and industry networking, how we connect together. Okay, then we go to the industry standard. Okay, and so on. So this is also the security one, the safety, how we make it safe inside the industry. Because when we're going to become smart, that means the factory or the industry used by what? By machines, right? No more human. So should be safety is more important, right? So we depend on the machines as well. Okay? So this is standard because everything we do, we have to do standardization, right? We cannot do, okay, I am doing for this, now if you write VHDL, you write first library IEEE, semicolon, right? Then that's mean using a standardization, library IEEE. That means this, anybody using VHDL using the same command, either here or in USA or any other country. Same language because it's standard, okay? So we finalize here about those applications. So going to see this short one about the FPGA, how utilize and in Industry 4.0.
Industry 4.0 and IoT across a wide variety of industrial applications in industrial automation, smart energy, and intelligent vision. In today's smart factories, Volterra is helping integrate secure, cloud-connected, programmable logic controllers, human-machine interfaces, and motor drives on a single chip, enabling edge analytics on the factory floor and edge-to-enterprise intelligence. The industry-leading Volterra Functional Safety Data Pack is enabling accelerated SIL 3 certification, helping customers achieve rapid time to market. Meeting growing 21st century energy challenges, Volterra FPGA technology powers the substation infrastructure at the heart of the smart grid, providing critical real-time substation controls with minimum response times. Volterra FPGAs also enable low-latency, high-performance synchrophasor applications such as real-time power grid state estimation, volt-var control, and wide-area frequency monitoring. Efficient management of two-way electricity flow from renewable energy requires FPGA technology to allow harshest environments, Altera is a proven partner to help designers build secure, connected, and power-efficient products for the industrial Internet of Things. For more information on Altera FPGA, SoC, and power solutions, visit altera.com/industrial.
So now I'm going to share some project that I did before, and still some of them already in progress. So I'll share with you, for example, this is this architecture already I did before 5 years. Yes, 5 years. So you see multiple processor. This processor, 2 processor already I built by myself, not using the NIOS 2. Why? Because NIOS 2 cannot support this application. This is about the tracking and navigation for AUV, hybrid AUV, autonomous underwater vehicle. Okay? So the NIOS 2 cannot support, so I decided to do the process by myself. Okay? So do different processor. This two different architecture. Okay? Slightly different, not 100%. So I'm utilizing filters. These filters not exist as IPs. So you have to build by yourself from A to Z, from scratch. Okay? So I didn't contribute to the filter algorithm, but I contribute to the filter implementation by using systolic approach. Yeah? So this is also, we have the other modules, the view modules, and the output one, input one, and some data buffers as well. Sure, with the clock generator for different level of modules. So this, like this architecture, cannot use one frequency. We have to use multiple frequency, multiple clock we call it. And multiple clock design system is very complex. Why? Because you don't have one clock support every module. You have different clock. That means one of them working in 100 meg, the other is working in 200 meg. So one of them working in 10 nano, the other is working in 5 nano. Right? You see the difference? So synchronization is more complicated in this system. Okay? So this is the processor, this processor architecture. Inside, I'm using the conduit, that means the floating buses inside the FPGA. Then this is the controller of this processor, and all this architecture put inside the chip, and this is the board. Okay, some of you come to my cube, yeah, my office. Sorry. So, okay, so you can see the board behind me. Okay, the red one and blue one. Those the board. Okay, then. This board already utilizes the whole system. If you can see, I used monitor connected directly to the board, the FPGA board, because no need to use processor now. No need to use PC to use monitor. You can use by just creating VGA, Super VGA controller, the signal control the view of image or data on your monitor. Clear? So this is one of the board. You can see this is the same board. Okay, I already utilized till now for some applications, especially for embedded. Okay, and this is one. By viewing the slides already I present here. Okay, this is the DE09, the smallest board in FPGA, the very small one. Me and my student already utilized in our 5P, especially and some of postgraduate students. They use this board, okay? Especially for example, for mobile, like robots, you can use this board. Where is the FPGA? Actually, this is the FPGA. Very small, okay? You see, this is your hand, and this is the FPGA. Okay, inside there is 24 kilo logic element. Okay, in addition to the memory and the other support component. Clear? So. Also, one of the project I'm using hybrid robot, like you see networking one, different robot. I put this picture for bird, different bird, right? That means different style of robot. Okay, can connect it together through the link, and so you see same one, different flying one as quad or X1. Okay, and with the ground one, UAV one. Okay, smart self-driving. One of my FYP also already did, not 100%. Still need to improve. Okay, the auto parking for critical condition. If you have a heart attack, you have dizziness, you are feel sleepy. How the car take overcome take autopilot and try to park safely aside. Clear? So this is also same application as well. The new one, reconfigurable SDN, self-defined networking. Some of networking people, they know about the SDN. So now I'm already working, and I have one PhD on this topic, how to make our FPGA reconfigurable, I mean, growth up according to the clients. If we have 10 clients, we have this design. And we have more client is income already inside the networking. The design itself reconfigurable by itself, without user interference, to make it bigger to serve a huge design, a huge client, and so on. So this is we call more auto reconfigurability. Okay, so this is the new project I'm working on. How to make it intelligent, respond according to the client already come to the in the network. Okay, smart building, how to make our buildings and cities more smarter, and so on. So this is the last one.
And now we're facing the next one, connectivity. But how can a company handle this? What does the industry of the future look like? Our experts have been wrestling with these questions for years. They know that the complete digitalization of the manufacturing industry plays a key role in the process. Why? That's simple. In the future, it will be more important than ever to operate quickly, flexibly, and cost-effectively. Product life cycles are becoming increasingly shorter, while product variants are becoming progressively larger. Just like large volumes, small quantities must be produced economically. Lead times will become shorter, so the delivery must become faster. For companies, this means that in the future, they must align their organization much more rigorously to meet customer needs. This can only be achieved if companies start today to digitize, automate, and above all, interconnect all processes. Not only within the company, but also along the entire value chain. This means a convergence of the various areas. Customers and business partners are part of the total process. The goal is to make all relevant data available anytime and be able to control the whole network of value creation in real time, from product planning and product and production development all the way up to production and logistics. Of course, data security must be assured at all times. Synchronizing digital and physical value streams not only increases productivity of companies, but also their efficiency, quality, and innovative capacity. The Industry 4.0 concept isn't new, but unlike before, we now have the knowledge and technology for it to become affordable reality. As you can see, the industry of the future presents us with many opportunities, challenges, and questions. But what's most important? What will you do? Let's shape the future together, securely, cost-effectively, with quality and efficiency.
Okay, finish. Just to conclude for you, the future of Industry 4.0 or high-performance application, sure that all engineers have to change to this technology. This is my perception in the future. Those working with full respect to the Raspberry Pi and Arduino, yes, for certain limit of application and performance, still you can do. For the upper of this, on the high level application, sure you cannot compete it with FPGA. Okay, so yes, this technology can use for a certain frequency, certain speed, but for high speed, parallelism, part cannot. Because now the trend of processor, they cannot just increase the processor. If you remember, the Pentium 4 Anyone remember Pentium 4? Pentium 4 is 3 point something gig, right? But if I ask you now, i7, the frequency, 2 point something, 2.2, 2.4 gig, right? So that means Pentium 4 is high performance than i7. What do you think? Sure, i7 is high performance compared with the Pentium 4. So, what is that? How to justify this? Because the processor architecture cannot just stick with the increase the frequency. We cannot increase frequency forever. Okay? We have to think in different way. To think now to use parallelism, even either spatial or temporal. Temporal, that means deep pipelining. Spatial, that means duplicating. Okay? So even we use less frequency, like 2.4 in i7, but we duplicate with 8 CPUs. Okay? So the duplication, that means parallelism, is the parameter to increase our performance, not just increase the frequency itself. Clear? So in our discipline, we have two solutions, either software or hardware. Do we have another solutions? We don't have either software or hardware. Yeah, sure. Hybrid can also. But which one the high performance one? Sure, the hardware, consider hardware as a high performance solution compared with the software. Which one the easier to do? Sure, software, right? So we have to balance. Software easier to design, easier to write the program, but hardware difficult to do, but high performance compared with software. So if you, this is depend on your character. For me, sorry, I just checked. My character, I want to be dominator. So I choose the hardware rather than software. So what the mean of dominator? Just I share one story with you. If you are working in the team and your colleagues, one of them to, for example, software guys and you hardware guys. So which one the leader to other? That means the software have to follow the hardware or hardware have to follow software. Normally, if the software written for hardware, so the software should be follow the architecture of the hardware, right? Clear? Very simple. Software follow the architecture, cannot architecture follow the software. Clear? So that means the dominator is the hardware guys. So later on, it depends on you as a hardware designer. If you want to make the job of the software guy difficult, you can do it by yourself. By what? Type the architecture for that guy. That means make it very fast response. That means very fast frequency. So the software cannot catch this frequency. Clear? So in this feature, please don't use it wisely. Don't use it to disturb your friend. For example, if you hate me and you are a hardware guy, then that means you want to make my job as a software guy difficult, right? So you make the architecture is very difficult. So as a software, I cannot write the efficient program to utilize your architecture, right? Please don't use your scale to disturb others. Remember, hardware is a dominator of the software, but please use it wisely. Clear? I just do brief. I'm sorry I take 1.5 hours. Sorry, huh? But just try to explore with you this some potential. My view, I'm sure that industry will going to utilize FPGA more and more. The application going to be reconfigurable rather than programmable. Clear? So this is my email. If you need anything, we can help you. Yeah, we can help you to do your projects. I mean, to help you to finish your project. Okay, sure, with knowledge. We will not do the project for you. Okay, we will help you to get more knowledge. Okay, then when you go, you finish your study. Either you will go to work outside industry or company, or you're working as an academic. You still have the enough skill and with cutting edge technology. Clear? So please do email me if you have anything to share or to do. We can discuss indeed about your problem. Okay? Thank you so much. And Raja, say, okay, do photo session, huh? Yeah. Thank you. So any question, by the way, I didn't ask. So any question about this information? I hope you are interested in this information. Maybe some of already knew. Just if you want to explore more, expand more, just let me know. Thank you so much. Rajan? Oh.